Well, folks, welcome back to part two. Forgot I only had 15 minutes there. Okay, so we were talking about how these four steps to hypothesis testing are going to be true for all hypothesis tests. Okay, so let's get on with it. Number one is state your hypothesis about the population parameter. Remember, we're talking about populations more so than samples. So, what is it that you basically believe to be true about the larger population? Okay. Second step is prepare. In other words, choose a significance level and test statistic, right? You want to check requirements and state the assumptions that you're making. You'll see that all statistics have certain assumptions that are required that they be met. So you'll want to be careful to pay attention to the assumptions of the statistic to make sure that that you can run that statistic with some degree of confidence. Okay, but remember this idea of significance level. It's usually going to be 0.05 unless you have a good reason for changing it otherwise. Okay. And then the magic happens here. You're going to compute to compare. In other words, you're going to compute the test statistic and you're going to find the p-value to measure the surprise. Now, I can tell you that, if this were a class where we were doing statistics by hand, if we were working out formulas and the like, then much of this would be where the math comes in, right? You would be hand calculating things out. There are generally sort of tables that one would use to find the p-value. But in this class, we're using StatCrunch. So essentially, what you're doing is you're using the computer to compute the test statistic. And the cool thing is that it also computes this p-value. So you're finding the p-values, just finding where on the output, right, that the test statistic and the p-value are listed. Okay, but here's the tough part. And that is interpreting what you found. Right? So remember, when you run these test statistics, they're really about whether or not you're going to reject, and look at this strange language, fail to reject the null hypothesis. Notice nowhere does it say accept the null hypothesis, and this is just sort of crazy sort of statistical language. So you're either going to reject the null hypothesis. Remember, the null hypothesis says that there's no effect. So it's like a double negative, right? If you reject the null hypothesis, then you're basically rejecting the idea that there's no effect. You see that? Or if you fail to reject the null hypothesis, right? Think about what that sort of is saying to you. It's saying that, hey, the null hypothesis has no effect. I can't reject the idea that there's no effect. So I'm kind of saying there's no effect. Okay. I know it's sort of awkward language. I didn't invent it. But it's sort of the way that we talk in statistical terms. Okay, but then the idea is to state the conclusions in the context of the study. Remember that you began this endeavor with plain English. You want to end with plain English, and so this is this piece about stating the conclusions in the context of the study. Right? If you've rejected the null, right, which means that you've rejected the idea there's no effect, and that means that you're probably going to say something about there being an effect with regard to whatever it is that you were studying. On the other hand, if you fail to reject the null, right, that means you're going to say something along the lines of having found no effect with respect to whatever it is you were studying. So it's really that last part that you need to end on. Sometimes people think it's just about finding the numbers and you're done. No, interpretation is extremely important. And in this class, since the computer is going to do the heavy lifting for you, you're actually going to be focusing more on the interpretation piece. In other words, once you look at that output, can you now translate that into plain English? Okay. So, what are the rules? How do we interpret? Well, if that p-value, now remember the p-value is an indication of the amount of risk of making an error. And we have said that we're not willing to risk more than 0.05. In other words, 5%. Okay? So if that p-value is less than our alpha of 0.05, once again, if you change the alpha, then it would be whatever that is. By default, it's 0.05. Then we're going to reject the null. Right? Remember, the null says there's no effect. And we're going to accept our alternative hypothesis and state the conclusion. Because what is that saying? That's saying that if the p-value actually suggests that our risk of making an error is less than 5%, then we're going to say, hey, I reject the idea there's no effect going on here, and I'm going to accept my alternative hypothesis, which probably proposed that there really was some kind of effect happening here, right? And I'm going to put this in plain English, okay? On the other hand, if the p-value is greater than alpha, so I'm saying that, hey, the probability of making an error is greater than 0.05, which is our threshold, then I've got to fail to reject the null hypothesis. In other words, I've got to pretty much, come to the conclusion that, hey, there's no effect happening here, right? And generally, this is where you can kind of, drop it here and just say, hey, there's no statistically significant evidence that you can make a conclusion, right? Or you could say that perhaps it suggests that there is no effect with regard to whatever your context is. Okay, so this is kind of how you do that interpretation. So the information that you get from step 3, you follow these rules to put it in plain English. Okay. So that's chapter 8. Let's pivot to chapter 9. And my focus here is going to be much more conceptual because essentially what we're doing with chapter 9 is we're introducing the first of our inferential tests, but we're really following these rules that we just sort of covered in chapter 8. So now we're just sort of focusing on t-tests. By the way, probably jumped a little bit too quick. All right, so chapter 9 is on inferring population means. Okay, so the focus here is looking at means. And so the way that we do that are through a thing called t-tests. And there are actually 3 t-tests that are introduced in this chapter. The first one is something called the one-sample t-test. Then there's something called the independent samples t-test. Sometimes people call them the 2 groups t-tests or 2-sample t-tests. And then there's the paired samples t-test. Sometimes this is called the dependent samples t-test. Once again, I'm sorry for all of these synonyms that are out there. But these are the 3 t-tests that are introduced in this chapter. Okay, so let's tackle the one sample t-test. It's a t-test that's basically used to compare the mean of our sample to this thing called the mu. Remember, the mu is the population mean. So basically, we just have a single group and we want to know how does our group compare to the population. Now, generally, we don't know what the population is, but we have some kind of estimate of that because all we're really working with is our single sample. So another way of sort of saying what we're doing here is we're kind of asking, is our sample deviant, right? Like, is our sample different from the population in some way? Okay. And so I generally leave the computing of this to another video, but I thought it might be helpful to kind of walk this through and show you kind of where things are at on the printout, okay? So we're going to kind of walk through how we could do something like this. First of all, we have our 4 steps, okay? We're going to state the null and the alternative. We're going to choose our alpha, 0.05. We're going to make sure the assumptions are lined up. We're going to compute the test statistic. In this case, we're going to compute a one-sample t-test, right? And we're going to get the p-value, and we want to compare that p-value with our alpha, okay? And then we're going to interpret it. We're going to decide if we're going to reject or fail to reject the null, and then we're going to write down the conclusion in the context of the study there. So let's suppose that we had something like this. We had 150 minutes per week of exercise as recommended. Okay, so that's kind of the mu, the population, if you will, right? And so we're interested, on our particular campus, do college students exercise more than 150 minutes per week? So what we do is we have 42 randomly selected college students that we have tracked their weekly exercise. So that's what you see over in the right column. Okay, and so we're basically going to be comparing this sample, right, to the population. Okay, and so we're going to compute to compare. Cool thing is this is sort of how we would do it with the StatCrunch. We would go to stat, choose t-statistics, choose one sample with data. If we have the data, right, it would look something like this. Okay, we're going to choose that first option up on our hypothesis test. Notice we put in the null mean, which is 150, because that is essentially what the population mu would be in this case. And then we run it, and we get something that looks like this. notice that we have the sample mean. So this is actually the mean of our 42 people. It's 152.92. And once again, but here's our t-statistic, but here's the probability value. Okay, now notice this probability value is 0.08. That's actually above our threshold of 0.05. Okay, so we would have to fail to reject the null that our sample is somehow different from this 150 minutes, right? So do they exercise differently from the 150 minutes? We'd have to declare that there's no effect here, right? There's no evidence that somehow they exercise differently from that norm. Okay, hopefully you see how that plays out. One of the other things that's sort of introduced in this chapter, which is sort of a throwback to chapter 7, is the idea of a confidence interval. Okay, so if you recall, confidence intervals give us plausible ranges for our population mean. Gives us a sense of the percent of all the possible confidence intervals that contain that population mean. And, you know, it's similar to the confidence interval that we did in chapter 7, which was around a population proportion. But here now we're focusing not on proportions, but actually quantitative variables, as in means. Okay, and so if we were, say, doing a confidence interval with the same data that we had, well, not same data, but a similar situation, we could do something like this: t-statistic, one sample. We set it up the same way. Notice this time we're actually choosing the second option, right? The confidence interval. And notice in the box levels where we would specify which confidence interval we want. Most of the time it's a 95% confidence interval. And lo and behold, we run it, and notice this time, instead of being given a p-value, we're given a lower limit, upper limit. The rule for deciding significance in this case is if 0 falls in between these limits, right, then it would be not significant. Notice that 0 does not fall between these limits, and so this would actually be evidence of a significant effect, right? So this would suggest that yes, our sample is somehow significantly different from the population with respect to their recovery times from the flu virus, right? If for some reason we had been treated, like if we're a hospital, we could brag about, how much better our folks are doing relative to the population. Or in fact, it may be the opposite. Maybe our people aren't doing so well relative to the population. Okay, that's what we basically have tested. Okay, so I wanted to kind of give you a sense of that. I'm going to hurry along because I'm running out of time. Let's see. So the independent samples t-test. So this is our second t-test. In this case, the independent variable is categorical, and specifically, we're looking at two groups. Okay, and the dependent variable is a numerical variable. So consider these examples here: male versus female test score. So clearly, the independent variable would be sex. Okay, and our dependent variables test scores, but notice there are two groups here, male versus female. Same thing, say Missouri versus Illinois happiness ratings. Okay, once again, we're comparing people on the Missouri side with people on the Illinois side. Okay, say SLU versus WashU students, comparing their SAT scores. Notice that in both cases, we're comparing two groups with each other on a numerical value. So when you have two groups, you're comparing the means, right? You want to use the independent samples t-test. Okay, and finally, then there's something called the paired samples t-test. Here we're comparing two numerical variables. They are paired in the sense that both variables are actually connected. So you have to be careful not to confuse this with the independent samples t-test because it's different. You might have two means, but in this case they're normally connected. So we might have the same people, but we're looking at before and after scores. Or say we have identical twins, right? We're comparing them, or say husband and wife, or older sibling versus younger sibling. In all of these cases, right, there's a connection between the scores. And that's how you differentiate the independent samples from the paired samples. If they are connected, right, then they're paired. If they're not connected, then they are actually independent samples t-tests. Okay, so this ends our lecture for chapter 8 and 9. Bye-bye.